Okay, square root review. Hey, you should have had an introduction to square roots in Algebra 1, and then also use them quite extensively in geometry. Okay, but it has been a while, so our objective for this lesson is to review the simplification of square roots of perfect and non-perfect squares, and to rationalize the denominator of a radical fraction. Okay, so you guys might be wondering what that word radical means, so we'll get in that lesson. So first of all, we're going to talk about what a square root is. Like many things in mathematics, we do things one way, and then we do them the other way, we undo them. Kind of like we start by taking 10 and adding 3. Well, then we would take and subtract 3 to get back to where we started. So we kind of do that both give and take. Same holds true with square roots. Okay, so first let's look at what a square root is. And to understand that, we need to know what a square is. When I square a number, for example, when I take the number 5 and I square it, it's putting a little 2 up top, 5 squared, and we get 25. Hey, so if I was given a 25 and I wanted to get back to the number here that I squared, that's where our square root comes in handy. So I would use this symbol here, which that symbol is called a radical sign. Okay, and so I would square root the 25, and that gets me back to my 5. So I square 5 to get to 25, and so then I square root 25 to get back to 5. Okay, so a square root undoes a square. So a square root undoes a square. Okay. So to help us with the squares, it helps to know our perfect square numbers. Okay, meaning when I take 1 and square it, what do I get? I get 1. So then the square root of 1 would be 1. When I take 2 and square it, we get the number 4, because 2 times 2. When we take 3 and square it, that's not 3 times 2, that's 3 times 3, we get 9. When I take 4 and square it, I get 16. These numbers are what we call the 1, 4, 9, and 16. Are what we call perfect square numbers, because they come from me squaring a whole number to get to them. Okay, so other perfect square numbers are 25, because that's 5 squared, then 36, because that's 6 squared, then 49, because that's 7 squared, then 64, because that's 8 squared, then 81, because that's 9 squared, then 100, that's 10 squared, 121 is 11 squared, and 144 is 12 squared, but ... I could keep going. I could square 13, square 14, square 15. Okay, these are the most common ones that we deal with. These ones from 1 to 12 are perfect square numbers. Okay, and so if I have a perfect square number that's one of these, then I know it's going to be, and the square root of a perfect square is a number itself. So when I look at the square root of 81, I'm asking which number squared is 81. So we look at which number times itself is 81. Well, 81 is 9 times 9, so it's 9 squared. So we can go ahead and we'll write the squares above it. 4 squared, that's 5 squared. 6 squared. So the square root of 81 is just 9, because 9 to the second is 81. 9 times itself. Okay, so the square root of 16. So let's look at our perfect square numbers. The square root of 16. 16 is the square of 4, so the square root of 16 is 4. Okay. All right, now the square root of 50. Well, if you notice the square root of 50, 50 is not a perfect square. It's in between these two squares, 49, 49 and 64. So my number is going to be in between 7 and 8. Okay, so this is going to be a number in between 7 and 8, the square root of 50. Okay, so what we do when we encounter a number that's not a perfect square is we break it up. We break it up into factors that are perfect squares. So we're going to break this up. So now I'm going to look at my perfect squares, and I'm going to see, can I multiply any of these perfect squares times something and get to 50? So can I take 4 times something and get to 50? I don't think so. 9 times something, 16. Again, you want to try to find the biggest one possible. Let's say 25. 25 and 2 is 50. So we'll rewrite the 50. Instead of the square root of 50, we'll rewrite it as the square root of 25 times 2. Because again, 25 times 2 is just 50. So in multiplying square roots, you can break them up into two different square roots. The square root of 25 times the square root of 2. And the square root of 25 is 5, so we're left with 5 times the square root of 2, which is just 5 times the square root of 2. That's as simple as it will go, because there's no other perfect squares that I can multiply to get to 2. Okay, I can't take 1 times 1 times 2, but that's not going to get me anywhere. So really, we don't use the 1 very often. But 4 times, I can't multiply 4 times something and get to 2. Well, I could, but it'd be a fraction, and we don't want that. So we'll just have 5 times the square root of 2. And if I was to get that approximately in my calculator, we can get the approximate for that. If I take 5 times the square root button is right there, so it's second squared, which makes sense. X squared and square root undo each other, so they're the same button. 1 second. So 5 times the square root of 2 is 7.07. Which we would expect the square root of 50 is really close to 49, so we would expect our answer to be close to 7, which it is, 7.07. All right, so now we have the square root of 32. Again, we break this up, so it would be the square root of, let's see, what multiplies to give me 32? 4 times 8. Let's see, do we have any bigger ones? 9, 16, 16, and 2. Ooh, 16 and 2. Again, you want to try to find the biggest one that goes into it. So 16 and 2. Okay, so the square root of 16 times the square root of 2. The square root of 16 is 4 times the square root of 2. So we get 4 the square root of 2. Okay, if you would have done it the other way and done 4 and 8. So there's another way of doing it, or if we would have used 4 and 8. Okay. So then I would have had the square root of 4 times the square root of 8. So then I would have had 2 the square root of 8, 2 times the square root of 8. But 8's got another perfect square in it. It's got 4. 8 is 4 times 2, so I can break up the 8 into 4 times 2. The square root of 4 is 2, so I'd have 2 times 2. Which again gives me 4 the square root of 2. So it just ended up having one extra step in there. I had to break up the square root twice. So if you can find the biggest perfect square that goes into it, you don't have to do it twice. Okay, you just do it once. Okay. So now the square root of 108. So let's find some perfect squares that go into 108. So if you're not sure, I don't know my 108 tables as well as my others. So let's take 108 and divide it by a bunch of stuff, see what goes into it. So let's try some of these bigger numbers. 100 won't work. Pretty sure 81 won't. What about 64? Nope. 49? Nope. 36? 36 and 3. We found it. So we can divide this, break 108 up into 36 times 3. So that would be the square root of 36 times the square root of 3. So we'd have 6 times the square root of 3. And then let's double check our 3. Are there any other perfect squares that will multiply in to get me 3? Nope. So we're done. 6 the square root of 3. Okay. All right, let's see number 6. Ooh, now we have a division. Okay, so here, just like when we had a square root with a multiplication inside, we could take the square root of each piece and multiply. You can do the same thing with division. So I can take the square root of each piece and divide. So it's the square root of 45 divided by the square root of 36. And so then you just simplify each of these individually and then see if you can simplify between the two. So let's simplify the square root of 45. Let's see, perfect squares in the square root of 45. 9 and 5, I think. And the square root of 36 is just 6. So the square root, so we'd have the square root of 9 times the square root of 5 all over 6. The square root of 9 is just a number 3. So I have 3 times the square root of 5 over 6. Since this is a multiply, it's a factor, I can simplify between the 3 and the 6. 3 goes into 6 twice, so I'll have the square root of 5 over 2. So there's how it simplifies. Okay. All right, now you've seen me do 6 of them. Now it's your turn. Pause the video, and I want you to do your turn problems 1, 2, and 3. You need to attempt every single one of these 3 problems. Write something down. Look at the examples previously and see if you can't follow my work, because we will be going over these in groups the next day in class. Okay. All right, so that's simplifying just plain old square roots. Simplifying square roots of perfect and non-perfect squares. Now we're going to do something called rationalizing the denominator. Okay, the reason we do this is we don't like radicals in the denominator of a fraction, because it makes it hard for us to tell how many equal pieces do we have. Because again, remember how a fraction works. This denominator tells me the number of equal pieces, and the numerator tells me how many of those equal pieces are we dealing with. We don't know how many pieces to cut it into if our denominator's a radical. So, like here in this example, here we have a fraction 3 divided by root 2. We don't like that root 2 in the denominator. I can't simplify that root 2 any farther to get rid of it. So we do what's called rationalizing the denominator. What we do is we actually multiply this thing by the number 1. Because we know multiplying by 1 doesn't change anything. Hey, but we multiply by 1 in a weird way. We multiply by 1 as a fraction. So if you think about the number 1, 1 is equal to 4 over 4. It's also equal to 8 over 8. It's equal to any number over itself. It's also equal to negative the root 2 over root 2. Okay, so I'm going to look to see what square root is in my denominator, root 2. And I'm going to multiply by root 2 over root 2. Again, this is just 1. That divides out to 1. So we're not changing the value of this fraction. We're just writing in a different way. Kind of like how we take the number 1/3, and I can multiply both numerator and denominator by 2 and write it as 2/6. 1/3 and 2/6 are the same amount. It's just written in a different way. That's all we're doing here, but now we have radicals involved. So now I multiply straight across. 3 times root 2 is just 3 times root 2. Root 2 times root 2, just like we could separate our radicals here into 2 separate ones, we're just going backwards and we're going to put them together. So this would be the square root of 2 times 2, the square root of 4. But now what's the square root of 4? The square root of 4 is just 2. So I can rewrite this as 3 root 2 over 2. So now I know I divide my whole into 2 equal pieces and I take 3 root 2 of them. So there's our final answer. We just want to make sure we don't have a radical in our denominator. Okay. All right, let's do it again. Here, example 7. So I look at my denominator, it's got a root 5 in it. So I'm going to multiply numerator and denominator by root 5, or root 5. So now I multiply across 1 times root 5. Well, 1 times anything is just the square root of 5. Root 5 times root 5 is the square root of 25. The square root of 25 is 5, so I have root 5 over 5. Okay. So now number 8, we have a division, so I'm going to break it up into the square root of 8 over the square root of 50. Okay, and now I'm going to simplify the square root of 8. That's 4 and 2. Perfect square. All over the square root of 50 is 25 and 2. So now if I take the square root of 4, that's 2, the square root of 2. The square root of 25 is 5, the square root of 2. But now we're multiplying. I've got 2 root 2 all over 5 root 2, but since we're multiplying, this is just 1. So this simplifies into just 2/5. No radicals at all. No radicals divided out in that one. Right, example 9. Okay, again, let's break these up. The square root of 20, perfect squares in 20. 1, 4, 4, oh, 4 and 5. So I have the square root of 4 times 5. Now 18. We've got 4, 9, 9 and 2. So the square root of 4 is 2. All over the square root of 9 is 3. Again, we don't like this radical in our denominator, so my radical is root 2. So I'm going to multiply numerator and denominator by root 2. So I'd have 2 times 5 times root 2. Again, I can put my radicals together and get 2 to the square root of 10. All over 3 times the square root of 4. So I'd get 2 to the square root of 10 all over 3 times 2, which is 6. My 2 and my 6 simplify, so then they're 3 times. So we're left with root 10 over 3. Okay. All right. Number 10. Again, let's try to simplify inside our square roots first. So 15 multiplies to give me 3 and 5. 4, and none of those are perfect squares, so I can't, no, 3 and, no, there's no perfect squares in 15. But there are in 12, 4 and 3. So I have 3 the square root of 15, all over 2 times 2 the square root of 3. So then now we have 3 the square root of 15, all over 4 the square root of 3. Okay. Remember I said 15 was 5 and 3? If I broke it up into the square root of 5 times the square root of 3, because I notice I have a square root of 3 in my denominator, and the square root of 15 I can break up into 5 and 3, so now what ends up happening is my square root of 3's divide out to make 1, and I'm just left with 3 root 5 over 4. Okay. I'm hoping some of this is coming back to you as we're going. Right, here for number 11, I'm taking 3 square root of 5 times 6 the square root of 125. Let's see here, 125, that might be able to simplify. I'm thinking 25. Yep, 25 and 7. So 3 the square root of 5 times 6 the square root of 25 times 7. So 3 times the square root of 5 times 6 times 5 times the square root of 7. So let's see, my number parts is 3 and 6 and 5. So I multiply those, 3 and 6 and 5, we get 90. Now my square roots are 5 and 7, multiply those, we get 35. So I have 90 the square root of 35. Let's see, do they have any perfect squares in 35? 35 is 1 and 35, 5 and 7. None of those are perfect squares, so I think we're done. Okay. So now I want you to do your turn problems 4, 5, and 6. So again, attempt every single one of those problems because you will need to have at least started them to discuss what we're doing in class tomorrow. Okay. So you need to do your turn 1, 2, and 3, and 4, 5, and 6, and come to class ready to discuss.